And again, I'd like to welcome you to our webcast today, Introduction to Elastic Block Store. Our presenter today is Miles Ward, who's a Senior Manager of Solutions Architecture here at AWS. Miles, you have the floor.
Aurora, thanks a bunch. And everybody, good morning. I really appreciate everyone taking the time to join us in reviewing what I think is a very, very important topic inside of the broader suite of tools from Amazon Web Services. The Elastic Block Store provides some very unique benefits for small businesses all the way up through web-scale startups and the largest enterprises. And I want to make sure that you come away from today's hour together with a much clearer understanding of how EBS works and which kinds of applications it works best for and the kinds of systems you can build on top of what it delivers. From an agenda standpoint, we're going to walk through really some definitions around EBS. What is that system? How does it work? What are the other tools from Amazon that it interacts with? Some places where you can use it. And then go through some key concepts that are really critical in understanding what we see most customers spending the most time around, which is planning and projecting and scaling and scoping their design of EBS inside of their application. And we'll talk through block sizes and IOPS and throughput and how to make sure that what you provision on top of Amazon is able to meet the needs of your application. And we'll go through an even more detailed view at some performance and availability tunings that you can do to ensure that your application goes as fast as you like and never stops going fast. So at AWS, I think at the highest level, there's really kind of two basic approaches to storage. Lots of different vendors do this different ways, but I think in most cases that's easiest to understand as a clear subdivision between storage of blocks, which is called block storage, or file system storage. The Elastic Block Store allows you to write individual zeros and ones into a block storage interface like a block device. So, for Windows users, that means things more like your D drive and E drive and F drive. For Linux users, those are locally mounted /SDA or XVDA kinds of drives. A drive or a hard drive, or these other kinds of labels are the right thing to think of when you think of EBS. There's this other storage model, object storage, which is really keys with really big values in NoSQL databases. Object storage is a really popular way to store data that doesn't change. So S3 and its archival brother Glacier is a system for storing the content that you don't make very many edits to, the pictures in your photo gallery, the videos, music, other kinds of data sets that don't shift. S3 has a bunch of cool behaviors in that when you put an object in there, that object can be made accessible to the web and can be served directly to the web. But for workloads where you intend to change the contents of individual files, S3 can present a lot of overhead and a lot of complexity. And in many cases, the software that you run isn't designed directly to interact with object storage of any kind, let alone S3. So block storage provides a much more standardized, much more accessible work model in comparison to the kind of newer idea of object storage. So what's EBS? How does this work? An important concept is EBS is designed as a persistent storage layer for EC2. So EC2 is where you're renting computers from us by the hour, and inside of EC2, one of the biggest and most important value propositions there is that you only have to turn on the computers when you need to use them, and you only pay for them when they're on. The hard part about that for lots of applications is that if you're going to use the local disk, what's called ephemeral storage, that storage is deleted upon stop or terminate of EC2 instances. And so that potential loss of data, limits lots of applications. With EBS, your storage can persist independently of the EC2 instance. So that means you can only pay for the monthly costs of EBS, which are very, very low for keeping, application state and local data and configurations and installations of content ready to go at a moment's notice when you want to turn that EC2 instance back on. EBS is also designed for very high performance, allows you to attach not just one remote volume, but potentially multiple volumes in order to store multiples of all the way up to 1 terabyte of disk space. So EBS volumes can be up to 1 terabyte, and you can attach several of them to EC2 instances for greater than 10 terabytes of aggregate storage. The system is also very, very secure. So because the EBS device isn't attached by way of a web accessible or even network accessible protocol, the virtualization layer that Amazon Web Services deploys connects to your EBS volumes through our control plane. And that connection then is only accessible from inside of your AWS account, dependent on your AWS credentials. So a very, very secure way to connect to storage. And because it's block storage, you can also encrypt that storage or encrypt individual files within that storage in a way that meets your best practices. We also have built, because we know that most customers don't like losing data, EBS to include a degree of high availability in its basic design. So every EBS volume is backed by more than one physical hard drive, and that backing ensures that if there's a single failure of a single disk, which, as we all know, at scale happens all the time, EBS is a service that can survive those kinds of individual outages. EBS is also made incredibly more durable by way of its integrated relationship with S3. So in the same way as you can save a picture or a video file, you can also save an image or a duplicate copy of an entire EBS volume. That's called a snapshot. Snapshots make it so that at any point in time, you can duplicate the written data on an EBS volume to S3 for recovery to a new EBS volume whenever you feel like it. So that backup process is available only for EBS volumes and not for local ephemeral disks, and is an important value proposition of the EBS system. We also deliver very rich metrics on the performance and utilization of individual EBS volumes. So where a standard ephemeral disk supplies simply disk and in and out data, an EBS volume has additional metrics like queue depth and I/O rates and other information that can help you diagnose, one, what the current workload is against your volumes, and two, potentially which kinds of new volumes you need or change in configuration that you need in order to be able to meet your performance or scale requirements. So what are customers doing with EBS? What's the use cases that we see deployed most frequently? And I think above even these sort of more specific EBS use cases for direct use of storage, far and away the most popular usage of EBS is to provide root volumes for Amazon instances, for AWS EC2 instances. The advantage there being that by using EBS-backed AMIs, which means that the instance starts from EBS rather than starting from local ephemeral storage, we enable the features of stop and start so that as a EC2 instance, rather than terminating it, deleting it permanently, we can temporarily suspend usage of the server and suspend the cost of the server while keeping those EBS volumes, including the root volume of the operating system, persistent. So below that, down looking at the storage layer that powers applications, EBS volumes get used to power numerous enterprise workloads. All of the major enterprise applications have clear direct dependencies on object storage. Certainly for aggregated applications like SAP, other ERP systems, other kinds of MRM or CRM, large-scale line of business applications. But as well, further down, all of the database tier applications. one of the things that you'll hear me say a couple times in the next 45 minutes is that if you're running databases, they should be on EBS, and they should be on a specific kind of EBS from us called provisioned-IOPS, and we'll go through what that means. But certainly, Oracle's database, Microsoft SQL Server, MySQL, Postgres, all of the relational databases, as well as the NoSQL databases like MongoDB, Couchbase, Cassandra, those are the kinds of systems benefit very strongly from high-performance provisioned-IOPS EBS storage. We'll go through that as well. Your applications, particularly distributed network file systems or other kinds of storage-related applications, benefit pretty strongly from the EBS service. And lots of different sort of gaming, social, and mobile and educational tools also have strong needs for strong data storage layers, including things like EBS. Most of your big data workloads, most of the applications where, as a user, you're chewing through terabytes of information to come up with an analytical result, those also fit very well on EBS. So a couple of key concepts. EBS exposes several different resources, and we'll talk through the mechanics of each of those different resources and when it is that you'd use individual products from EBS, how those products cost, and how to understand the decision matrix between them. So first choice, and the thing that you need to evaluate for each time you're going to build an EBS volume, is whether you'll use what's called a standard volume, or what often gets referred to as just an EBS volume, or a provisioned IOPS volume. You can see that written as PIOPS sometimes, or PIOPS EBS. So standard EBS volumes are designed for really the root volume workload of EC2. So imagine that workload. Just like the hard drive in the computer that you're probably watching this webinar with, that hard drive does a lot of work when the computer turns on. It must read the operating system and all of its configuration files and the dozens of applications that are started to provide things like your web browser and these other tools. Similarly, the servers that you run in EC2 have a big burst of reads that happen when they turn on. And then following that, just like the local disk in your laptop or your desktop, there's a lot of use for that root hard drive swap. So that means that when you run out of memory, you may need to burst a bunch of small block writes to storage in order to make sure that applications remain stable in the presence of memory exhaustion. So we built the standard EBS product to deliver exactly that behavior. It's available up to a terabyte, and while having a very significant write cache out front of the storage layer, which enables that kind of swappy bursts of writes at a steady state over benchmarks running greater than 2 or 3 minutes, you'll see an average I/O performance much closer to around 100 IOPS, or input-output operations per second. So 100 IOPS, while plenty fast for the vast majority of operating system volumes, root volumes, for data analysis or databases or big data systems, that can seem pretty anemic. And we have customers that are expecting not hundreds, but thousands of IOPS. And so we built a product specifically designed not to be the root volume of EC2 instances or the storage volume for large-scale file systems, but instead an EBS volume designed for databases, designed to run the kinds of transactional workloads that are very I/O bound or very IOPS bound. So provisioned IOPS allows you to define exactly how fast an EBS volume will operate. Today we'll tolerate any provisioning from 100 IOPS all the way up to 4,000 IOPS per volume. So again, that's 40 times faster steady state than a standard EBS volume. Really significant boost in performance in comparison to a standard EBS volume. So we strongly recommend all database workloads, all NoSQL workloads, barring those that are sort of closely oriented around very, very large object sizes, more like distributed network file systems or large-scale values for key stores. All databases, all NoSQL systems typically benefit hugely from the use of provisioned IOPS. And it's really important that those systems are designed to take advantage of that tool. So provisioned IOPS volumes allow a pair of choices when you design and deliver that volume. First, just like standard EBS, you pick the amount of storage that's available in 1 gigabyte increments all the way up to a terabyte. And then you pick the number of IOs per second, or IOPS, that storage volume can do. And there's an important limitation there where you must have at least 1 gigabyte of storage for every 10 IOPS provisioned. So that means you need to have a 100 gigabyte volume for a 1,000 IOPS drive, or a 400 gigabyte volume for the maximum 4,000 IOPS device. So that's available not only through our console, you can see a picture of the configuration tool there, but also through the direct use of the EC2 API, or CloudFormation, or OpsWorks, or even now through our AWS marketplace. So that's an easy to access and easy to deploy system. Provisioned IOPS also has some far stronger commitments around consistency. So one of the big things that we heard from customers was that it doesn't really matter if something is impossibly fast. If regularly the speed of that varies, I have to anticipate and measure against the lowest average speed, and that's what I use to bound the designs for my workload. So provisioned IOPS will deliver within 10% of the IOPS performance provisioned 99.9% of the time over a given year. So within 10%, it's not going to go any faster than what you provisioned. So you're looking at up to minus 10%. So for a 1,000 IOPS volume, 99.9% of the time, which is the vast majority of the time, the actual I/O performance on that volume will be 900 IOPS or higher. Now there's an important little asterisk on this measurement, and we'll talk about this in a little more detail going forward, but for database transactions, recognize that at 1,000 IOPS, that means that you're spending a single millisecond for each operation. So given how frequently those IOs happen, again, 1,000 of them in a second, it's important that your application is actually able to request 1,000 IO transactions against disk every single second. In order to be able to maintain that kind of throughput, most applications will build a queue of work requests against storage. So you can measure that queue. It's called queue depth inside of both the EBS volumes themselves and typically the applications that you use. A requirement of meeting this consistency goal is a queue depth of 1 for every 200 IOPS provisioned. So that means that you'd have to maintain a queue depth of 5 for your application workload for an individual volume to really see that 1,000 IOPS number come out the other side. So if you go forward to looking at what this looks like compared to other storage options, on the left-hand side, we're doing a burst of 4K random reads against a standard EBS volume. On the right-hand side, we're doing that same workload against the physical ephemeral solid-state storage in our EC2 High-1 4XL instances. In the middle, you have provisioned IOPS. So if you look on the left-hand side, you have, several results in the 200 IOPS mark. You're seeing a benefit from the write cache that exists, ensuring that there's sort of memory available to serve up both the sort of read and write operations. But if you look in the middle there and at the top, there are some results that are significantly lower than that 200 mark. You go from 235 down to 196. At the very top, that's a 180. In the middle there, a couple of IOs a couple of seconds at 76 and 73 IOs. So you're seeing pretty significant variability, and even inside of the periods where you're looking at, 200s, you're seeing, 220, 209, 196, 213, 235. So in the range of 10% variability second to second on the IO performance of an EBS volume. With provisioned IOPS, if you look in the middle column, you're seeing much more like 0.1% of performance variability over the test period. So 1010, 1009, 1011, 1010, 1010, 1010. So for this workload, this happens to be a test for MongoDB, you're seeing a couple of orders of magnitude tighter consistency from provisioned IOPS EBS in comparison to standard EBS. And even though the standard SSD volumes on the High-1.4XL instances are clearly incredibly fast, able to deliver hundreds of megabytes a second of throughput at tens of thousands of IOPS, you'll note they still exhibit the kind of variability that standard EBS and other kinds of physical devices present. So you see, probably an average in the range of 64,000 or so, but there's a dip to 61 and another dip to 61 and another dip to 52. So those are, again, in the range of 10+% variability events inside of the storage workload. And there are some applications that tolerate that kind of variability just fine, and there are others for whom that would be crippling. So another way to see this difference is to look at end-to-end latency for transactional events. We measure this using CloudWatch. So this is a chart you actually get inside of your AWS console. So for a workload involving sort of a benchmark test for relational database storage, you'll see on the upper axis, in the range of half of a second to sort of a quarter a second, really sort of hovering around a quarter second, 100 milliseconds, something like that, latencies, and variabilities up into the sort of half millisecond or a half second range, little bumps and spikes. And then in the middle of this test, you get a little bit of a bloom where you see a pretty significant latency burst where EBS is either flushing cache or doing some other kind of functional work. And that variability can be really impactful to database performance or other kind of application performance during those periods. If you look at provisioned IOPS, that's the lower section. One, clearly there's no spike over this time period. But if you look a little more closely, even the variability that it does show is literally an order of magnitude tighter band. The upper area is in half-second increments, and the lower area is in tenth of a second increments. So we're seeing really steady, 0.1 second, sort of latencies end-to-end for operations against storage. And that kind of consistency of latency in the tight band of operations is an important feature of the provisioned IOPS system. So when should you use provisioned IOPS? Again, standard volumes are designed for running EC2 instances, for boot volumes. For applications with really bursty I/O patterns, no work, and then all of a sudden a bunch of work, or things with sequential I/O access where you're reading the entire volume into the system. Functionally, everything else, everything that is random I/O bound, should be run on provisioned IOPS. A big driver for that is the difference in the pricing model between provisioned IOPS and standard EBS. So in standard EBS, you pay us a tiny fraction of a penny for each I/O done to storage. So if you do no actual transactions against storage in standard EBS, you pay no transaction cost. And if you have a big burst of transactions, you pay for those individual I/Os. With provisioned IOPS, you pay us a penny per I/O per month, steady state. So what that works out to is a lower rate for the cost of an individual IOP because you're paying us upfront for an I/O every single second of the entire month. And so if you don't use those IOPS, you lose the value associated with them. So it's really designed to operate these kinds of high-performance databases that are running 24/7. But in the same vein, you're saving money if you have that kind of steady, consistent I/O workload that standard EBS would probably charge you quite a bit for. So how to pick and how to understand what volumes to use where and when and how many of them and how big is a place where we get a lot of customers with a lot of confusion. So let's introduce a couple of building blocks. First, on EBS, whether that's standard or provisioned IOPS, each operation that gets done is done by way of a block event, a block operation. And those can be thought of also as IOs, an individual IO. So each application emits IOs potentially of very different sizes. There are maximum sizes that vary by operating system and file system type, and there are minimum sizes associated with the same. It's very typical to see some applications, particularly some databases, operate at relatively small block sizes. 2 and 4 and 8 and 16K tend to be the typical sizes for applications. For example, SQL Server is 8K, MySQL is 16K, Oracle is configurable to 2K. Each of those different sizes relates to the amount of data that is changed in a single operation. So you can imagine a 16K write where the change that you're making to a database is simply to flip a 0 to a 1. You write roughly 16,000 times more data than you need to. So certainly there are advantages to having small block sizes for databases with those kinds of tiny transactions. Conversely, if you have applications that are writing whole binary long-form objects, the big hashes of metadata or huge blog posts, free text fields are going into databases, you may need to consume multiple block operations to do a single functional transaction from the database. So beyond blocks, there's also, and those are sort of defined by the file system and how the file system is configured, and then also supplementarily defined by the application. On EC2, you have a network connection between your EC2 instance and the EBS service where the storage that those operations are going to be done to you exists. And then on that storage, you have the performance of the storage itself. And that performance is measured in two values as well, the number of IOs, random or sequential, that the storage can perform, and the throughput to that storage medium. So that's an important concept. So let's take the first example of standard EBS. Standard EBS tolerates, again, like we explained, roughly on the order of 100 random IOs per second. Now, the flip side of that is that you can expect on the order of 40 to 45 megabytes a second of sequential throughput across an EBS volume. The reason that works is that the IOs, one, are not random. So there isn't a seeking function that happens in order to deliver those IOs to storage. And two, you'll tolerate much larger blocks. So an individual operation is maybe 256K or 512K rather than a smaller, more random 2K or 4K or 8K write. So you can imagine that the math problem you're trying to solve is that for a given application, given the block size of the operations that it does and its degree of randomness versus sequential operation, how do you get enough throughput to move the bytes of data, and how do you get enough random I/O performance to move the actual IOs across the wire? And you can imagine that each of these are potentially constrained. So if you have some individual IOs from the application to the storage system that are much bigger than your block size, those will be multiple IOs to storage rather than a single IO, and you have to sort of keep track of that. You also have the maximum network throughput between EC2 and EBS. And then you also have the throughput and IOPS performance of the actual EBS storage that you provide. So any of these three values can be a constraint, and all three of them must be correctly configured in order to be able to design an efficient and high-performance EC2 EBS system. So a couple of little bits of math, and probably a place where lots of folks get confused. Networks are measured in megabits per second, and disks tend to be measured in megabytes per second. So inconveniently, there are 8 bits per byte, and we use the megabits numbers to define things like the network throughput from what's called EBS optimized instances, which we'll talk about in a bit. So I can make an M2 4x large, that's an instance from EC2 that's pretty hefty, enabled with what's called the EBS optimized flag, and that provisions a 1 gigabit or 1,000 megabit per second connection between that virtual machine and the EBS fleet. Measured in megabits, that's 1,000. Measured in megabytes, that's 125 megabytes per second. And when you do it in megabytes, you can start to do a better job of understanding that the block sizes are also measured in bytes. So let's say, for example, you're running MySQL on EC2, and you run the standard block size format for MySQL, which is 16K. So if you're using 16K blocks, you can run roughly 7,500, I think it's 7,800 and some, individual block operations across that 1,000 megabit limit. Similarly, if you reduced the block size of your operation, that means each I/O is a quarter of the size, you can do 4 times as many I/Os across the network link. So that is how you understand the network bandwidth between EC2 and EBS. Provision or EBS optimized volumes or EBS optimized instances are available in both gigabit for the largest instance types and 500 megabits, so half that fast for M22XLs and M1 larges and other instances. So how to get into designing for your specific application is a combination of picking the right instance type, the EBS optimized flag, and the right number of EBS volumes to deliver either the throughput required or the I/O performance that's required. So block size. On provisioned IOPS, on the higher I/O storage, we specifically measure and limit individual I/Os to 16K in size. So if you're running MySQL, that's pretty convenient. It's the same size as the MySQL default size. So that means that if, in that previous example, if I had a M24XL with gigabit, I could provision 2 4,000 IOP provisioned IOPS volumes and feel really confident that I can saturate the network link and my provisioned IOPS volumes with 16K I/Os to deliver just shy of 8,000 IOPS from the system. So the throughput that you get on a provisioned IOPS volume, so if you want to think about it in terms of megabytes per second, is just a math problem where you multiply the number of I/Os that you do by the block size that you're writing. So let's assume that you are writing huge blocks, 256K or other kinds of big blocks. The provisioned IOPS system will actually subdivide that write into however many 16K blocks are required. So it's really important to be careful if you are building custom applications. You certainly don't want to write 17K blocks. That means we'd consume more than a single write for each transaction. We from a throughput standpoint, won't penalize you as badly as you'll consume 2 16K operations for each one. But it will be more complicated for you to plan the exact performance that you can extract, which is why we've so tightly aligned with the database locked block operation size event. Part of that, part of the workload feedback that we heard is that, for operations that are in a short-term way sequential along these kinds of volumes, things like restoring the backup for your database or copying a new database file onto a server, will allow bursts of sequential I/O, bursts of throughput to the provisioned IOPS system in the range of 40 megabytes a second. So that gets you to the same rough performance as a standard EBS volume, so there isn't any kind of performance impact or slower delivery of backup or storage or things like that. So again, you could do on a 2,000 IOPS, provisioned IOPS volume, 2,016K reads. You could do 1,032K reads, 564K reads, and upward from there. And you'd get, if you measured it from a throughput standpoint, pretty consistent 32 megabytes a second, again, assuming a queue depth and the EBS optimized flag that would give you enough network bandwidth to deliver that. So, again, to sort of to provide detail on that queue depth, which is a metric that you can see from our consoles in CloudWatch, you do have to maintain an average queue length of 1, rounded up to the nearest whole number for every 200 provisioned IOPS inside of a given minute. And so another requirement of the consistent delivery for provisioned IOPS volumes is the use of the EBS optimized flag. So an important part there, the EBS optimized flag provides a dedicated link, a more consistent link between standard EC2 and VPC EC2 as well, and the EBS fleet. That linkage is also required to maintain the consistency goals that we outlined at the beginning of this talk. So if you want to be at that 99.9% value, you have to have the EBS optimized flag to turn on. Now, we've had some questions. Does EBS optimized help if I use standard EBS volumes? And the answer is yes. So if you are throughput limited to disk, you need additional network bandwidth just to do sequential operations. EBS optimized works for both provisioned IOPS storage and standard EBS. So performance, how to go faster, how to make systems that scale. Given the couple of different numbers for performance and the couple of different systems that are involved, there are a couple of different building blocks that get used to build high performance, consistently performant, and easy to backup system. So first, really strongly recommend, in almost all cases it makes sense where you have a storage-oriented workload to use the EBS optimized flag and keep track of as we continue to grow the fleet. We've actually added to the list that's listed here now the C1 extra large instances support the EBS optimized flag as well. So you can also take a look at, as you're looking at sort of performance, make sure that you actually specify enough IOPS for the workload. We have plenty of customers that expect, just like auto-scaling from EC2, that somehow magically the storage will turn out to be as fast as their workload needs it to be. If you don't actually configure it that way, it won't go any faster than you've designed. So another important measure is to look at that network connection as a critical bottleneck in the system. So you could easily provision vastly more provisioned IOPS storage than your network connection would allow you to utilize. So, I mean, it's just a 0 on that previous command. If we look back one slide, this little thing that says ECU create volume, if you create 10 of those volumes at 4,000 IOPS, that's 40,000 IOPS of storage performance. But it also requires a number of megabytes a second of throughput that at 16K you would not be able to do on a 1 gigabit connection. Now, you may have a workload that uses very small block operations, and 40,000 might make sense, but you may need more network bandwidth still than that 1 gigabit link. So we have another class of instances, the cluster compute family. So that's CC1, CC2, CR1, HI1, and HS1, which all support higher bandwidth connection as a part of their high-performance 10 gigabit network linkage. So cluster compute instances, all 5 of those that I named, will actually provide 2 gigabits of network throughput to storage. So that means that any of the values that you can calculate out for a 1 gigabit link, you can roughly double those. So you can get really, really high I/O performance from those storage systems, or you may want to look at applications that use smaller block operations or evaluate your workload to make sure that you fit into those sizes. So we keep talking about multiple volumes, and we have lots of folks that get confused about how to use those. In Linux, that's typically done with a piece of software called MD-ADM, and the MD-ADM configurations are literally about a line long. And really there are only sort of two choices in MD-ADM or on the Windows side using the disk management utilities that would allow you to construct what are called redundant arrays of independent disks, or RAID. So we see most customers, when aggregating storage, given that EBS already is duplicated, has presence on multiple physical devices, you see lots of customers choosing RAID 0. What RAID 0 does is combine multiple volumes into a single logical volume by spreading the data across them. Now, it creates no duplication of that data, which means that you get the full performance of both disks at the risk that if a single disk fails, the whole storage system will fail. So it's important that when you're operating in RAID 0 that you're either using an application that is duplicating the data at the application tier, potentially across multiple servers, or that you are working on data that you already have a backup of, or another kind of high availability strategy implemented. If you don't have either of those things, if your whole system runs on a single server, probably safer to use a model called RAID 10. Now, RAID 10 has a minimum of 4 disks because you're creating a striped set and then mirroring that striped set. So RAID 10 allows you to take an individual volume that fails and while still using the system, move that disk out of rotation and move a new EBS volume in. That happens at the cost of typically a 50% or slightly greater than that reduction in aggregate write performance from the system. In some applications, you can continue to read from either side of the mirror, which means that you'd see 85, 90% of the read performance associated with a RAID 0 of the same type. So that just depends on your specific workload. For example, MongoDB is very well optimized around the sort of RAID 10 multi-read system. Other applications aren't quite as well optimized. So certainly worth testing on your side to figure out whether your application requires the disks to be combined in this way, or if you're using something like a distributed network file system where your application may have native management of storage volumes integrated. For example, SQL Server will tolerate multiple different physical drives and distribute workloads like fog files and data files on separate drive letters. If that's the case, you don't have to RAID them together necessarily in order to use multiple disks. So another important component, we have lots of folks that benchmark and test and run evaluations against storage. The EBS and Provisioned-IOPS system use what's called a loose provisioning model. And so there's a pretty significant performance impact to the first write or read to an individual block in either EBS or Provisioned-IOPS storage. The typical model for ensuring that this write performance doesn't impact benchmarks or otherwise adversely affect the system is to just go through and read every single block in the storage system. So for Linux users, that's a kind of a one-liner DD command. For Windows users, an easy way to do that would be to do a complete format of the entire disk, and there are other kinds of approaches there as well. So if sort of consistent performance, particularly for sort of benchmarking or things like that, is critical, this is a great step. If you just want to get started using the system, just anticipate that as your storage utilization inside of an EBS volume grows, you'll likely find that there's a little bit of a slowness at the very, very beginning of usage that quickly goes away. So another component there is understanding this is one of the important differences between block storage and object storage, in that with block storage, you provision how big the disk will be and then start using the parts inside of it. With object storage, you simply should give us objects and we charge you based on that. So for standard EBS and provisioned-IOPS EBS, you pay per month, prorated at a daily grain, for utilization of storage at a gigabyte grain. So you would say, I want to use a 35 gigabyte standard EBS volume. That's charged at 10 cents a gigabyte a month. You'd be charged $3.50 for that volume. If you use provisioned-IOPS storage, that charge is slightly higher at 12.5 cents a gigabyte a month. So if you look at the process of making these kinds of systems highly available and durable, you likely want to take snapshots. You can create snapshots of any EBS volume. Those are duplicated to S3. It's also important to recognize that EBS volumes exist within an individual availability zone. So let's say US East has today 3 availability zones for net new customers. If you've been running with us for a long time, you'll see a couple of other availability zones. You may have as many as 5. So your EBS volumes are necessarily located in one of those availability zones. In order to move it to a different availability zone, you must copy it to the centralized system called S3. So that's called taking a snapshot, same as backing it up. Once backed up, you also have the ability not only to create a new EBS volume in a different availability zone, but you can also copy that snapshot to a distant region. So that moves the data over the internet to the other side, potentially the continent or the planet, and then in the same way you can create a new block device, a new EBS volume out of that snapshot. So snapshot performance. When you create a snapshot, when you take a snapshot of a volume, every block that makes up that volume is evaluated against a copy of that block, either if it was full of zeros because you hadn't written anything there, or a copy of that block from your most recent snapshot. And that evaluation is done to allow an incremental backup of the storage system. So any net new blocks that have changed since the last snapshot, or all blocks if you've never taken a snapshot, are then duplicated to S3. And in the same way, the next snapshot that you take will be built on the previous snapshot. So every additional snapshot, particularly if you are taking snapshots at high frequency, typically is reading fewer and fewer blocks off of storage. Any block that has net new data during the process of the snapshot will have lower sort of access performance during the period while it's being duplicated to S3. So the more data that is, the longer the snapshot takes. The longer the snapshot takes, that means there's more data that's affected from a performance standpoint. Customers at the far extreme of having hundreds of gigabytes of data on an EBS volume and having never run a snapshot can see between 15 to 50% write performance, in particular write performance impact against the storage system for the duration of the snapshot. Full 1 terabyte volumes and the full maximum amount of dirty blocks since the previous backup can take days to snapshot. So it's important that you test early and confirm the exact durations that it takes to do your backups in practice. So you should plan for those snapshots then. It's important to evaluate not only what frequency with which you'd like to do snapshots, whether that's every 15 minutes or every week or every hour or every day. And then also if you have a multi-region high availability story, you potentially want to plan for those kinds of regional transits because the copying process also takes time. So what does scaling look like as you grow? If you look at your average database, we can use Postgres as an example. Even at the smallest workloads, you're building a WordPress blog for your aunt, and you want to make sure that the database is fast enough for all of the pictures of her knitting. You still should use at least EBS storage, simply because the disk persistence and the availability characteristics of an EBS volume are so much better, and the backup process to S3 is so valuable. As you move into what I'd call sort of normal production scale, the use of databases for real workloads, you'll typically move to provisioned-IOPS storage. We really strongly recommend that all database workloads run on provisioned-IOPS, even if that provisioned-IOPS is provisioned as small as 100 IOPS of performance. You'll make sure as you grow not only to increase the provisioned IOPS for an individual volume, you'd increase that by taking a snapshot and creating a new volume at higher performance. You also potentially would be moving to larger instance sizes and enabling things like the EBS optimized flag to ensure that you have enough bandwidth to and from the system. As you get up to the maximum, to sort of extra large size performance, you may want to look at more exotic techniques like rating the EBS volumes together, like using the largest instances and then all the way up into our cluster compute instances to give yourself better bandwidth, and configuration tunings at the operating system tier and your application tier to ensure that you're creating the kind of queue depth that's required to saturate those storage systems. And again, all of this is to say that, we've covered in 50 minutes what on other kinds of systems can potentially take, weeks and months of study. These systems are much easier to use than some other kinds of environments, and so it's a really straightforward story around delivering the performance that's frankly world-class. Being able to deliver tens of thousands of IOPS of storage performance for NoSQL and relational database workloads puts you into the class of the kinds of databases that run things like, Amazon.com. So with that, really recommend and encourage everybody to get started on EBS today. There's a lot of information and documentation available that was used to generate this presentation. We have not only detailed information about the provisioned IOPS system and some approaches and best practices for benchmarking EBS if you're trying to compare it, but there are numerous case studies from partners and internal and external users around the performance of EBS and its really significant positive impact on large-scale databases. I'm always available on Twitter at Miles Ward, or you're more than welcome to email me at miward@amazon.com. That's it for the presentation today, but I'm excited. We've got some great questions that have come in through the Q&A system, eager to follow up with everybody. Aurora, do you want me to take those, or are you going to queue those up?
Yeah, why don't you go ahead and just read through those right now and then go ahead and answer them as you would like. While you do that, I do just want to remind everybody to please go ahead and fill out our survey today and let us know what you thought of Miles' presentation. And you can access that survey by clicking the widget down there at the bottom of your browser, and it'll open up in a new browser. And just let us know how you enjoyed the presentation today. And with that, Miles, I'll hand it back to you to answer those questions.
Awesome. So a great question came in around, folks in testing and short-term workloads have seen standard EBS volumes able to deliver thousands of IOPS, often faster than provisioned IOPS, and they're wondering if that's something that's expected. And given the way that standard EBS is designed, particularly for small block operations on the right side of the workload, you can potentially see bursts typically up to 1,000 or 1,200 or so IOPS, again on the range of a minute or 2 or 3 minutes or 5 minutes or something like that. That kind of performance boost, again, is super helpful for the kinds of workloads like swap from memory or other kinds of pieces. Really encourage and expect that is exactly what you'll see. What you won't see is that kind of performance steady state over hours. And most of the database workloads that we see have persistent, hardcore, significant workload, and that kind of consistent delivery of I/O performance is what's critical. Another place where provisioned IOPS will typically run circles around standard EBS is on the read throughput, particularly random read performance. So it'll be very difficult to extract on the order of even above a couple of hundred IOs from a standard EBS volume. So another question that's asked about the sort of best practices handling of EBS volumes, it has to do with how to take snapshots of multiple volumes at the same time, particularly if they're rated, so that that snapshot is consistent. So it's first off important when you're doing this kind of work, and a best practice from us, that you'd quiesce writes or pause write operations to the storage system. That if you're only having a single application that interacts with storage, could be as easy as, quiescing a database, or calling an XFS freeze on the file system, or an ext4 freeze, or unmounting the volume, or other kinds of functions that prevent write operations and ensure that any write cache at the operating system tier has been flushed. There are some tools that help with this stuff. Elastic, as a part of the Ubuntu project, has EC2 Consistent Snapshot. That's a tool that can help folks manage EBS volume, multi-EBS volume, RAID EBS volume snapshot processes. So another tool from that team that's probably important to take a look at, we have a lot of folks that have found that if you're taking snapshots every 15 minutes, that ends up being a very large number of snapshot IDs. There's typically not a negative price or cost component of that. You're paying only a tiny fraction of the cost of the volume, in that it's only the incremental differences between the snapshots that each ID has for you. But it can be difficult to figure out which one you want to keep and to automatically delete the ones that you may not need as time goes by. So there's a GitHub project, again from the Elastic team, called EC2 Expire Snapshot, that can make that part of the system easier to use as well. So there's a question here that said, if EBS drives on the back end are RAID 0, or RAID 1, then wouldn't software RAID 0 on top of it create 10? And if not, why not? The first piece is RAID 1 has a very explicit definition, and the EBS system is not natively RAID 1. It's in a lot of ways better than that, and provides a durability characteristic that I think is better than the RAID 1 spec, but it's an incorrect assumption to make that we use the RAID 1 specification to defend EBS volumes. In the same way, if you use software RAID 0 on top of standard EBS, you have typically the same kinds of durability mathematics, same kinds of sort of expectable mean time between failure as you would with a RAID 10. The issue is with a RAID 10, once it fails, there's something you can do about it. So in this situation with EBS, we're the ones who have to do the sort of swap out of the individual pieces, and it's still possible, if there's a concurrent failure of multiple devices on our side, that you'd see an EBS volume fail. So it's more like RAID 110 if you run RAID 10 on us, but we have many customers who want sort of that extra degree of isolation. So there's a question that's come in, does AWS on its own take backups of EBS volumes? And the answer to that is no. Independent of the high availability work that's done on standard EBS that we just described, there are no backups other than the ones you take with the snapshot process. So very important to snapshot that disk. So another question, and this is super critical. I want everybody to turn the speakers up. This is a long-standing misconception, and it asks, does a 1 terabyte EBS volume translate to a dedicated 1 terabyte disk spindle? And the answer to that is no. 1 terabyte volumes are old, and you really might have trouble going to the store and buying a 1 terabyte disk, and we buy a lot of disk. So the performance characteristics of standard EBS include a degree of variability at all sizes, and the provisioned IOPS system is the only way to get to a significantly higher consistency of disk performance. Using multiple volumes in RAID 0 does not improve the consistency of performance. RAID 10, you can see some improvement in the consistency of performance, typically by moving to the lowest common denominator. The issue with that is that comes at roughly 50% overhead, and as a result, it can make much more sense to simply use provisioned IOPS, a system designed to deliver consistent performance, as the best practice. We've had a couple other questions that I'll follow up offline, but we are at the top of the hour. I really appreciate everybody's good questions and hope that this is a great place for you to start in getting started with EBS.
And I just would like to thank you, everybody, today for joining us, and thank you so much, Miles, for the great presentation. Have a great day, everyone.